Alrighty, it's recording.
Okay. Good afternoon, everyone. It's Ed Roberson, Home Team Inspection Service. I'm going to share my screen here in a minute and start the presentation, but I just want to say up front, anytime in this today that you have any questions or if you have interesting experiences to share, just jump in. Don't hesitate to jump in. Often, if you've got a question, it's something other people are wondering about, and if you have some interesting experiences to add, just feel free to add those. I'm gonna share screen now, and you should see the presentation. Understanding HVAC systems. Like I said, I am Ed Roberson, Home Team Inspection Service. My license number and also my radon certification number. We'll talk about that. We've got that session scheduled for next week, so we'll talk about that then. So today, this will give you an idea. We'll kind of give an overview here, but the purpose when I designed this course or presentation, I should say, is to provide realtors with good, valuable information, some overview on how the system works, but some very real information and assistance when you're out looking at houses with people, some things you can do to help you understand what you're looking at for the HVAC systems. So we'll start today, thermostat types, zone control, how the systems work. We're going to go through an overview of the typical systems in the triangle so that you know how things like heat pumps, gas furnaces, split system air conditioners, package units, why is it a package unit versus a split system, etc. We're going to identify those system types. We'll talk about sizing the system for the space and determining the age of the system. There's some real good information for agents on the nameplate, and I'm going to help you understand how to and where to go to interpret that information. We'll talk a little about fresh air ventilation, which is a more and more of a thing as houses get tighter and greener. How do you get more air into the home when you need it? And there are some very real times you do. And then what I call the refrigerant apocalypse. It really is only apocalyptic for older systems, and we'll go over that some. So thermostat types, you go far enough back, and some of us can remember just the manual thermostats. Nothing happened until you physically manipulated that with system settings, with a switch, or manually moving the thermostat. All those functions were manual, and it was a type specific to a system. In other words, you had one type for a heat pump and one type for a furnace. They were not programmable. Then we progressed into the digital thermostats that were programmable for time and temperature settings. You could set, what you want the temperature overnight, and then what you want it to be when you get up in the morning. What do you want to change to once you leave home, the house is empty all day. And then you could do that differently. Weekdays, one setting, set of settings, and then weekends another when you're around more. And those are switchable for different types of systems. In other words, if you take that face off the wall, the base that was physically mounted to the wall has a series of little micro switches in, and you set those micro switches in order to have the functionality for the system you've got. If it was a heat pump, you had one setting. If it was for a gas furnace, it had another setting, and that determines what you see on the thermostat for the mode types and that sort of thing. And some of these can be operated remotely, Wi-Fi enabled. You could operate them from your smartphone, etc. And then you move ahead to where you have what are called the smart thermostats. Nest is one type, but there are those that are integrated with home control systems. They may talk to your other systems in the home, like your security system, and all of that is typically accessible remote via an app. You can lock it, unlock it, set the temp up, down, turn systems on, off, etc. And these were just one part of that smart home technology, where things like the Alexas and the smart home devices. You can tell them what to do, they can tell it what to do. And sometimes these things can be too smart for home inspectors. We very often will get to a home and the seller has forgotten to unlock it so we can access it. And so then we turn around and call the listing agents. We have that info to call the seller to unlock it so home inspector can get our job done. And typically what happens, within about 5 minutes, we've got access, because fortunately they can do it from their phone. So then zone control, we'll talk about a little bit. More and more, as systems have gotten more efficient, you can do more with one system. There was a time, you go back, if you had 2 levels in a home, you had 2 different systems operating that. And then as they built these systems more efficient, you can take a single set of HVAC equipment and condition multiple levels or multiple zones using zone control. And what that simply is a zone control board. And you've probably seen these in attics or basements, close around the equipment. And what happens here is you'll have thermostats for the different zones. And a zone, in its most simple form today, might be a 2-story house that has one set of HVAC. So you've got a thermostat upstairs and a thermostat downstairs. Those 2 thermostats speak to this zone board, and then the zone board controls the zone dampers. That's how, if you want 72 degrees upstairs or downstairs and only 68 degrees upstairs because nobody's up there all day, this is how you can do that. You can set the different thermostats. The thermostats talk to the zone board. The zone board then controls the dampers. So you see in that supply ductwork, as that system runs, if the zone 1 damper is open and the zone 2 damper is closed, then you're only going to get airflow into that zone 1, and you're not trying to do everything everywhere at the same time if you don't want it. So also be aware too, you run into this occasionally as an agent. Some of the older systems, and you really stopped seeing it probably mid-90s, but you go back far enough and we'll still see a few of them here and there, where a home has 2 levels, but it only has one system and it only has
Did he drop out for y'all?
I'm trying to figure out if it's might be his computer, because I think it froze up.
I heard a loud beeping right before it happened, like
Me
something
too.
drastic just occurred.
Let me see if I am messaging him now. I might give him a call.
Yeah. I lost him, so.
It's a great day, Keller Williams Realty Platinum. This is Katie. How can I help you? Sorry, you guys. I do not know what happened. I was trying to get a hold of him real quick. I hope that everything is all right. I'm trying to get his phone number up real quick to give him a call.
Hey guys, a little action adventure here. Something's going on with the power system. The whole house power was clicking in and out. My uninterrupted power supply started buzzing. So let me get back to the screen here.
We wondered if you were okay.
All we heard was loud
no
beeping,
problem.
and then you were gone.
yeah. I'm not sure. I guess the power company, they've been working on the signals up at the intersection. So I don't know if somebody touched the wrong wire or something. I think we were, I remember where we were. I was talking about the last bullet here, required on system replacement. Those older homes that only have one system and one thermostat, there's a code requirement from about 2000, and I'm trying to remember sometime in the 2000s, where the code requires if when that system is replaced, the HVAC contractor is bound to add a zone control system and a second thermostat. So if you do end up in a deal with a house where you've only got one system, one thermostat, just be aware when the time comes to replace that, and in addition to the $5,000 or $6,000 HVAC system equipment replacement, the zone system's probably going to be another $2,500, $3,000. So that's something that's a savvy agent can help their client understand when they're evaluating a home and what it would. I mean, it is what it is, and it really is necessary, because if you've spent much time in a home like that, you'll know if that thermostat's downstairs, that upstairs is always too hot in the summer and always too cold in the winter, because you're actually controlling the system from downstairs. So it just makes good sense anyway. Let me open that, get back where I was here. All right. And that zone control board, it may look like this gray board here, and nowadays we see them even more often with just a clear cover. You know, you just see the electronics. It's got some indicator lights that really some zone telling you what each zone is doing. But these boxes are typically in the attic or in the basement or something. You're not around them anyway. But what those zones dampers are, this is what they actually look like when you've got a main trunk of the HVAC coming off the system, and then you see a duct going one way and a duct going the other way. And there's the little motorized damper. That's just the damper operator. The damper is actually a big flat plate inside that turns 90 degrees to go wide open or full shut. And that's what when we talk about zone control, that's what your actually does the job. So conceptually, for you real quick, without it getting so technical that it's too boring, to give you an idea how the air conditioning system works. What you're doing is with refrigeration, you're removing heat, you're absorbing heat from the room into the refrigerant that's passing through the coil. As you blow air across it, it's absorbing the heat from that air and changing in the process. It's changing from a liquid to a gas. In other words, the heat in the air is making that refrigerant evaporate from a liquid to a gas. And then you transfer that outside where you're taking it and giving off that heat and changing it back from a gas to a liquid. And those reasons explain why we don't run the air conditioner in cooler weather, as you know, in home inspections, because in that cycle, as you're going from that low pressure gas in that cycle there, you see hot on the right and cold on the left. As you're going from the evaporator down to the compressor, you don't want that to travel to that compressor as a liquid. In other words, you want enough heat that will evaporate that refrigerant, because if it travels back to that compressor as a liquid, you can damage the compressor. So the evaporator is the indoor coil in air conditioning, and the condenser is the outdoor coil. And you know, if you stand by that condenser outside in the summertime, the air blowing off of it is so warm. Well, that's what that fan is doing then, is it's transferring the heat out of that refrigerant into the outdoor air. And that very simply is how air conditioning works with principles of refrigeration. Your gas furnace, I really need to update this and kind of share with you. This is an older, more standard furnace. The more efficient furnaces, high efficiency furnaces look a little different configuration of this, but the basics are the same. In this system, your basic components here are going to be the burner section, which is in the middle here. You know, that's where your gas is being burned from the burners. The heat exchanger then is where you're drawing air from the area, and you're sucking it through here with a combustion fan across that heat, and your combustion products are traveling through here and then traveling out the flue. Well, in the process, you're heating up this metal of the heat exchanger, and then you're blowing the house air from the air handler that you see at the very bottom. You see how the return duct comes back through, and then you're blowing air across that heat exchanger and then out into the home. So you're drawing heat off of that heat exchanger with the house air and blowing it into the living spaces, and that's the source of your heat. And this also explains why you're always concerned about the integrity of that heat exchanger, and why with a gas furnace or anything that's combustion in the house, including having a garage, you want to keep those CO monitors, carbon monoxide monitors, located where they should be and operating properly. Because if anything breaches this heat exchanger, then you're getting the combustion products of this combustion process into the house air, and that's where you can get the carbon monoxide and that sort of thing into the house. So that's why we also are in our inspections are reporting on the integrity and the location of carbon monoxide monitors. The rest of the system then is just your ductwork and your air handler, you know, where you're drawing the air from and where you're blowing the air to. Then in the more efficient, high efficiencies, you can use sometimes, very often, you're using what's called direct vent furnace. And this would be a similar concept to your direct vent fireplace flue also, where you are actually looking at, you see this kind of hood sticking out the side, or sometimes it's sticking out the roof. You're actually a pipe inside a pipe, so that if you look at this head, you draw the air incoming through the back of this head into one pipe, and it's concentric. It's a pipe inside a pipe, and then you draw that into the house. Oh, wrong button. You draw that into the house of that pipe, into the system, combust it, and then you vent it straight back out the other pipe. And that's what we call direct vent. You're drawing the air for combustion from outside, and then exhausted and combustion products back to outside. And you don't need any air from combustion from the living space. And in fact, in houses where you have sealed crawl spaces or sealed attics, you have and you have a combustion system, you have to have a system like this. You have to be able to pull combustion air from outside the home. And so with new stuff, they construct it properly, but where you get into an issue sometimes is if someone has upgraded something. They've either changed, let's take crawl spaces for as an example. We had a home that I inspected not that long ago that they had updated and sealed the crawl space. Well, when they did that, they failed to convert to a direct vent furnace. In other words, they were still trying to draw combustion air from that crawl space and exhaust it outside. Well, what you've got then is you've got a very limited amount of combustion air in that sealed space. You need free flowing fresh air, unlimited supply in order to run a furnace. So anytime you have an existing home that has a crawl space or an attic with a furnace in that's drawing air from that space for combustion, and you decide to seal that space, you also have to fix that furnace system to accommodate so that it can draw air from outside. So that's something to be aware of in renovations. And it was a case where I believe, if I remember correctly, in that home, that HVAC system in that basement had been replaced, I think, after the thing had been sealed. So when the guys were sealing the space, they knew there was a furnace there drawing air from the space. That should have, the business they're in, they should know better than to come in and seal that space without advising, hey, you need to do something about this HVAC. Conversely, when the HVAC guys came in to replace that furnace, that crawl space was already sealed, and they turned around and replaced the furnace with another like in kind that needed to draw air from the space. So that was a case where both contractors dropped the ball. So don't always assume they're putting two and two together. The HVAC guys came in and did their job without thinking about how the environment had changed. So that's something to be aware of as an agent as you're looking at houses where renovations may have been done. So when we talk about heat pumps, then you really are doing nothing more than adding this reversing valve that simply reverses the flow of the refrigeration. So you reverse the tasks of the two coils. So in this particular case, this is configured the same as what you saw with the air conditioner, in that this is in air conditioning mode now. So your indoor coil is cold and your outdoor coil is hot. But if you reverse this valve and you reverse the cycle of this flow, this becomes your hot coil, this becomes your cold coil. You blow your house air across it, and that's how your heat you get your heat from your heat pump. And we'll talk a little more about that with respect to the heat strips, auxiliary heat, and emergency heat here in a few minutes too. But that's the major components of the heat pump. You're just literally adding one piece of equipment to that system that enables you to reverse those coils and reverse the cycle. then, you see what the units look like. When you walk up outside and see that outdoor unit, it's going to essentially look the same. Sometimes you can see that reversing valve down inside this, and I'll show you a picture of that in a minute, but not 100% of the time. I see one every now and then where they've got the reversing valve indoors. And that's what the reversing valve looks like. We've got a sketch coming up that'll help you kind of make sense of what that ABCD do there, but that's how you reverse the cycle. That is a discrete component. So here is your four-way valve in both of these drawings. And here we are in air conditioning mode over here and in heat mode over on the right. And you see all you've done is move the piston of that reversing valve to reverse the cycle. I'm not going to get too far down in the weeds on this, just to help, I just demonstrate it to give you an overview of how the systems work that we typically see in the triangle. And this is being recorded, I believe, if I haven't before. I think Katie's got all of these presentations. If not, we can certainly share those, and you can dwell more on this when you want. And I don't know if I said it in the beginning, but I'm available to answer questions, guys. You just feel free to reach out, send me a text, a phone call, an email. Always happy to field questions to help you guys do your job. So in that heat pump, we are in a zone of the country where if you get much further north from us, you don't see heat pumps anymore, because there's not enough, the weather's too cold, there's not enough heat in the outdoor air for conversion. And heat is a relative term compared to what the refrigerant can do. So down to about 30 degrees, there's enough heat in the outdoor air still for that refrigerant to do its job as it's going through that cycle. Once you get below that, you are going to rely on what's called the auxiliary heat in that heat pump. And that is a mode that happens automatically when the demand exceeds the heat pump capability. In other words, the outdoor air is so cold that the heat pump can't do its job. And so when that outdoor temp is lower, the heat pump can't convert heat. But also there's a second function when extra demand is required. In other words, if you've had heat pumps and you live with them, if you ever walk by your thermostat and you see that message aux heat on, well, that means the heat strips are running. And that's one of two reasons. One, it's just so cold outside that the heat pump can't keep up by itself. Or the second is you've told that system you want more heat than it can give in the time. You're looking for a lot of heat right now. And the example of that would be you're going to go away for the weekend in the winter. And when you left on Friday, you turned the thermostat down to 65 because you're not going to be there all week. You come in on Sunday evening, all weekend. Then you come in on Sunday evening, you bump that up to 72 degrees, and you're telling the system, I want everything you can give me right now because I want this house to be 72 degrees just as rapidly as possible. Well, if you came in and you bumped it from 65 to 66, and when it caught up and shut off, and then you bumped it to 67 and it caught up and shut off, if you went 1 degree at a time like that, that heat pump, the heat strips wouldn't kick on because the heat pump would, to the extent that it could, would do the job. But when you come in and in this case, give it that 7 degree differential, you're telling that system, give it to me and give it to me now. And so what it's doing is it'll kick in those heat strips. It's literally like a big toaster coils in that system that fire up and add heat, and you're catching back up. And once that heat system, in this case, once it got to 72, the heat strips would cut back off, and then the heat pump would just cycle on and off as it needed to. If, however, you're down in that temperature where the heat pump can't do its job, the heat strips are just going to stay on. Heat strips will kick on until the house gets warm enough, it'll cut off. And then, the whole thing will cut off, but you'll be heating with heat pumps once you get down to those, with heat strips, once you get down to those lower temperatures, because the heat pump just can't do its job. You go into the northern part of the US and you won't see any heat pumps because there's not enough heat in the air. You go extreme southern parts of the US and you won't see any gas furnaces because heat pumps can do everything you need the most efficient way. Here, we've got a mix of both. And, in some of our more temperate times, days when we're in the 40s and 50s, you're probably not running the heat strips at all during the day. They may kick on some at night, but if you're like us and you bump it down at night, maybe they don't have to run at all. But in these cold spells like we're going to have coming up, you're going to be running heat strips a lot. Normally, your heat pump's your most efficient, energy efficient system. Now, let's talk about emergency mode. We're using the same heat strips, but it's a bit different situation. If you have a heat pump and you go to your thermostat and you step through the modes, you'll find off, cool, heat, emergency heat. Well, emergency heat is a separate mode, and you would use that, you would manually set it to that in the event that your heat pump just fails. Your heat pump's not doing anything, it can't do anything, but you don't want to freeze and you don't want the house to freeze. And you're going to get an HVAC contractor there just as soon as you can. In the meantime, this is a source of heat. It's going to be the most expensive source, but at least it's heat. It keeps you from freezing the pipes. It keeps the family from freezing. And hopefully you can get an HVAC tech there very soon. But that is a manual setting that uses those same heat strips, and you would never use that. You would never use that mode except in an emergency. So we'll cycle through here and look at some of the system types that we have in the triangle. Split system air conditioner with a gas furnace. The air conditioner is like I showed you in that first. It's just the indoor equipment, the outdoor equipment. You got refrigerant lines that run between the two. And then the furnace is going to be natural gas or LP gas. If you're in on on a gas system, with the gas lines and gas meter, you're going to be running natural gas. If you're in a rural area where you don't have a gas system, you're going to have a bottle of some type and be running LP gas. And then in this picture, actually, the top and the bottom left really kind of show you everything, because the top is the outdoor coil. If you look over here on the left in that bottom left picture, that's the evaporator. You show it here, you see the whole evaporator. Well, that's where the refrigerant line is going back and forth and doing its job. And then in this section is the furnace, the gas furnace. And then in this section is the air handler. So the air handler is drawing air from the house, from the return vents, and just coming right through these. So when you're burning heat, your heat source is here. When you're cooling, your cool source is here, and you just use the same air handler to move that air through the home. And the rest of the system is just ductwork and registers and filters.
Ed, I'm not seeing the drawing.
You're not seeing the pictures and the...
No, sir.
What about everyone else?
I can see them. I'm not.
What's on the screen right now is the 4 pictures of the outdoor unit and the 3
and it
indoor
says
units.
split system AC with gas furnace.
Yes.
Yeah.
Okay.
Yeah, Joanne, I'm not sure what.
It may be the way I just had my Zoom, so I'm okay now. Thank you.
And I'll definitely send out these slides too, Joanne, so that you'll be able to reference back to them if you need to be.
Okay, sorry. Thanks.
Yeah, sorry, Joanne. I don't have any idea what's different there. Then we have a split system heat pump and air conditioner, where you've taken the gas furnace out of the equation and you're heating with a heat pump, like I showed in that cycle, and an air conditioner. You've got indoor equipment and outdoor equipment, so it's a split system. And the heat pump just reverses the refrigerant cycle to reverse the coil service, and the AC works the exact same as split system air conditioner. This is, like I said before, an efficient heat source down to about 30 degrees, but you do need the backup heat strips for auxiliary and emergency. These systems typically are, well, in this area, very likely when you get outside of the municipal areas where you have gas service as a utility, by far most of the systems are heat pumps because people aren't fooling with LP gas bottles and that sort of thing. But they're also very often installed upstairs in larger homes that may have a gas furnace downstairs. And the reason for that is when you're heating that downstairs area already, that heat's rising. So you don't have that much heat loading requirement upstairs. And so the heat pump that's conditioning the upstairs space just doesn't have to do that much because the space below it is already heated. Split system heat pump and air conditioner with a gas furnace auxiliary emergency. What this has done is simply adds a gas furnace inline instead of those electrical coils. We don't see these very often, and usually they weren't original equipment. Somebody had that furnace installed. We don't ever see them installed that way by builders or we don't see that many of them. It's not a bad idea. It's more expensive because you've bought more equipment, but it would pay for itself over time because you're using the two most efficient heat sources. You're using a heat pump when your temperature is high enough that can do the job, and then you're using gas, which is the second. Gas is, I say, the second most efficient. Gas is way more efficient than heat pump once the outdoor temperature gets so low. And like I said, we only really usually see these as a retrofit. I don't have a picture here because just picture a gas furnace in line between next to that indoor equipment of the heat pump. Split system air conditioner with a hot water furnace. You guys, if you haven't heard of them, you will sooner or later. We don't see that many of them anymore. They were much more prevalent in the 80s and early 90s, and they're generically called an Apollo system. So when you hear someone talk about an Apollo system, this is exactly what they're talking about. And in this particular instance, I did an inspection where they had all this equipment in the garage, the hot water heater and the furnace, air conditioner, everything was in one place. So it was handy to provide a picture for this purpose. This could be, most often we see them where the water heater is in one area and then the HVAC equipment is either in a crawl space or a utility closet or something like that. But what this system is a conventional air conditioner, a conventional split system air conditioner. You've got your condenser hot coil outside and your evaporator chiller coil inside, and that's in line in this picture. If you see where the big insulated line comes down out of the ceiling and goes into the lower part of this compartment here. Inside this compartment is your chiller coil right here. And then the upper part of this box here is your hot water coil that you're going to blow air across for your hot water forced air furnace. And the way that works is you have to have what's called an Apollo type water heater, and many manufacturers make them. This one happens to be, you can see its label, it happens to be an Apollo. But what you've got, and let me minimize this so I can point here to you. What you've got, if you'll notice, in this water heater, you've got your normal hot and cold water lines in and out of the top of this, like every other water heater. But in addition, you've got these other two inlet and outlet lines. What you've got inside this is a big coil sitting in this tank of water that is a closed loop that then cycles water through this loop. So your hot water heats this up. When the house needs heat, you open a valve, turn on a pump, and you're pumping water out of the top of the hot zone of this water heater and through this coil, blowing air across it, and then returning that water back to the water heater. These systems, like I said, you don't see them very often anymore. They seem to have been more prevalent in townhouses. When I see them, I'm typically in a townhouse. Sometimes it's in a crawl space, but very often it's in a utility closet indoors, and they're quiet. There's no combustion. It's very easy to compartmentalize them in a utility closet. And the systems seem to work fine and last a long time. Now, one coincidentally, because of the error, because of the era that they were built and installed, most of these places that we find them still have polybutylene plumbing, because that was in that era from the 80s and early 90s when poly was very prevalent. So usually when somebody's looking at this, they're looking at quite an old system, and they're looking at polybutylene piping. And of course, anytime, whenever you need a water heater, that's going to be a more expensive proposition, because these are more expensive. Like I said, these systems seem to last a long time. And really, if your water chemistry is good, there's really nothing to mess them up, because really what would mess these up as much as anything is scaling or buildup inside the pipe that might hurt the heat transfer. But we see them; they seem to, they heat well. They really don't make them anymore, but you'll see one sooner or later. Now you'll kind of understand better what you're looking at. Now, all of those systems we were talking about were split systems. You had equipment outdoors, and you had equipment indoors. And I know you're all familiar with package units, but you may or may not understand why they're called package units. The reason is everything, all of the HVAC equipment is in that package. Your AC condenser, your in this case, we're looking at a gas furnace. So your condenser, your evaporator, your gas furnace, and your air handler are all inside that package. Same equipment and function as a split system, but all of that equipment is located outdoors. We'll see these very prevalently in the older homes where the crawl space really isn't high enough to accommodate any equipment. So when you add a system like that, you want to convert that house to central air. All they had to do was run ductwork through the crawl space and add registers in the floor. Easy to do, set the equipment outside. And that ductwork does require a crawl space, or occasionally you'll see someone who will run a duct from that up the sidewall and into an attic. I guess if you're go far enough back that you've got a house on a slab that didn't have central air and you want to add central air, that's kind of your only way. These can also be used as a rooftop unit. So we see them a lot in commercial or in multifamily buildings where you'll have equipment sitting on the roof. And then all you see on that foundation wall is ductwork coming in. So that could be in a furnace, or it could be a heat pump. And in this case, you see the heat pump. Again, all of your equipment is in a package, and you've got nothing but ductwork going into the home. Here's an example of one. You remember I showed you or talked about a split system air conditioner, or excuse me, split system heat pump with a gas furnace in for the auxiliary and emergency. This is built that way. This was designed and built that way, all in one package. So you got your heat pump, your air conditioning equipment, and your gas furnace all in that package. But the gas heat is only used in auxiliary and emergency in the place of heat strips. And again, that's using your heat sources in the most efficient manner. When the temperature is high enough, you're using heat pump. You get down to where the heat pump can't do its job well, and that gas furnace will kick in. And that leaves us with the ductless, what's called ductless HVACs that we see in the area. On the left is a mini split. I'm sure most of you have seen or heard of mini split systems. That's the same equipment as a split system heat pump. You've got the upper part of that photo is mounted on a wall indoors, and the lower part is outdoors, and all you've got then is refrigerant lines in between. These do a very good job for a limited area. In other words, where we would typically see them in the triangle is where someone has taken and finished a small, maybe converted an attic to a bonus room or something, and it did not have any original HVAC. Well, you just put a mini split in the area and you take care of it. The other example we may see is where people added onto a home and maybe added a master suite, and the easiest thing to do was condition that suite with a mini split. We've seen where outdoor space was converted to sunroom and then put a mini split in there. They're quiet, they heat well, they cool well. They're not terribly expensive. I think these run around $3,500, maybe $4,000. So they're not cheap, but they're usually in our area, in my experience in the US, they are typically used where you have created some space that's not served by your original HVAC system. Now, I'm told that in Mexico, Central America, and in Europe, houses are more designed in zones where you may have 2, 3, 4 of these systems, and the house was designed intentionally to be zoned and conditioned with mini splits. So there's, and depending on relative cost and efficiency, we might see that here at some point, but they do a job very well. Then the middle is what's called a through wall unit. This is what you see in 99% of your motel rooms, where you've got the system in the wall, and you walk over, you manually turn on the heat or the air conditioning, and that's electric heat with air conditioning, very similar to a wall air conditioner. And then you have the old window units. Those could be, you can go to Lowe's and buy those that have electric heat and air conditioning, or the old traditionals were air conditioning only. So you'll see sometimes we don't see many window units anymore. Very rare. The through wall units, I'll give you an example of where I see those. You will see those in some of the townhouses, like the much older townhouses that were built in the 20s and 30s. One good example is over around some of that stuff over around Cameron Village. There is the crawl spaces are about 15, 16 inches high. So and you've got like a 2-story townhouse. So even if you could put some equipment underneath, which you can't, how would you condition the upstairs? Well, what I found is they put one of these in the rear wall at each level, so that you're conditioning the whole level with one of these through wall units. Mini split would do that job better, but I'm sure these systems were put in these townhouses before mini splits were widely available. Mini split would be the answer today. So then identifying the systems. This is where we get into how can you tell what the system is when you walk into a home, which is important. That's some real world where the rubber meets the road when you're walking into a home with a client. And among the many things that you want to determine is, what system do we have here? What type? How old is it? Who made it, etc. So the first thing you can do is you go to the thermostat, and if you turn on that thermostat, you scroll through the modes and you see nothing but off, cool, and heat, you've got a furnace. If you see off, cool, heat, emergency heat, that emergency heat mode tells you you've got a heat pump. Now, those thermostats may or may not have an auto mode. You see more and more where the thermostat has an auto mode, but I left it off the list because it doesn't matter whether the auto is there or not. If you have emergency heat, you've got a heat pump. If you don't have emergency heat, you've got a gas furnace, except for those rare cases where we find that they've got the wrong thermostat set up for the system. I found a townhouse that was a rental that had a heat pump in it that was 20 years old, and there was no emergency heat function on the thermostat. So I don't know what those poor people were doing when it got too cold outside, but you kind of get in a disconnect then between the people using it probably think they have to live with it like it is, and the people who own it either didn't know or didn't care. But we came along, in our inspection, we found that you had a furnace type thermostat on a heat pump system. Well, now, if you remember talking about those digital thermostats and the smart thermostats, they're programmable. That's a very easy fix. It's not like you have to replace the thermostat, but if you get into older systems, you may have to. Well, if you get into older systems, you probably need to replace the thermostat anyway. So when you go in, emergency heat or no emergency heat is your first clue to the type system you've got. Then when you look at the components, a furnace is going to have an exhaust flue or a direct vent flue. It's going to have a gas line. That's always either going to be iron pipe or corrugated stainless steel tubing. And it's going to have electric conduit to it, whereas a heat pump is only going to have the insulated refrigerant lines and electrical conduit. It's not going to have any gas pipe to it. It's not going to have any kind of flue coming into it or out of it. And those are things that are just impossible to miss when you stick your head in the attic or something like that. If there's no flue there, it's easy to determine. So share with you a few interesting things that I've seen. This house, and it was actually, if you recall a few slides ago where I showed the outdoor package unit that had the gas furnace integrated in with the heat pump. This was the same house. In this one house, we had a wood-fired boiler outside, and you had loops to where you could run auxiliary hot water and an auxiliary HVAC heat coil, water heat coil in that house. So they had the package unit dual fuel hybrid. They had the boiler, wood-fired boiler, and they had an LP gas generator. I don't know what they'd been through or were expecting, but that's going to be the last functioning household in the apocalypse for sure. So sizing the system. What's the right size system for the space you're in? You actually have trouble if it's too big or too small. We'll talk a little bit about what those are and sometimes some of the symptoms. Old school rule of thumb, 1 ton per 500 square feet. So cut and dry, 2,000 square foot home, you put in a 4-ton system. It worked fairly well for a lot of years because you needed more conditioning because the houses weren't very tight, before caulking and better duct insulation and frankly before insulation. I grew up in a house that when my family moved into it, there was no insulation. There was no insulation in the ceiling, none in the walls, none in the floor. And so back in the day, you needed more heat to just to survive. And that was well before the caulking and better duct insulation and better home insulation and before green building and all. But if you get a system that's too big or too small, either one can be problematic. Too small, it's just going to run more continuously. It may not condition the air. It may not be able to it's just always lagging behind. It just can't catch up with the space it's in. It's not going to last as long because it's running all the time. Too big, you're going to be short cycling, more wear and tear, and more repairs. The second thing with short cycling is the system will not properly dehumidify the air. One thing that happens naturally as you're conditioning that warm air and cooling it is you're removing humidity from that indoor air in the summertime. And if you ever walk into a house and your first sensation when you walk in is it's cool, but it just feels kind of clammy, that's most likely what you're experiencing. That system is not dehumidifying properly, and you can get into all kind of problems with that. That extra humidity in the air. Two things. One, you're going to keep bumping the thermostat further down because you're just not comfortable raising your power usage. But that humidity is also going to do things throughout the house that you don't want to happen. So if you ever walk into a house and it feels cool, but there's just something feels wrong, start asking questions about sizing of the system. Could be too big. In fact, we had one just this past summer that we walked in. That was our first sensation, and we asked some questions, and we had some other issues with the crawl space and all that kind of went to the overall. But it sure enough, that was one of the really big hits. Was that system was just sized wrong. The HVAC guys confirmed that. Again, too big is just going to cost more to purchase. Bigger equipment's going to cost more, and it's also going to cost more to operate it. So needless expense if you don't need something that big. So then they moved on to the modern, still kind of ballpark method, where you started taking into consideration, in addition to just the square footage, how many holes are in the walls, how many windows and doors, how many people, what kind of body heat loading do you have? And they started factoring that in, but it still wasn't right. The right way today is called manual J method, and that's a complex calculation. They use software. Nobody's sitting there with a pencil and paper and calculator doing this. They're loading all of the information about the house into that system, and that's telling them then, here's what you need, here's where and why. And you're looking at overall, how is the house built? What are the materials? How much air loss are you going to lose through the walls and through the ceiling and through the floors, and how many windows and doors, and how many people are, what is the house designed for, people wise, etc. So you take all of that information, load it into the system, and it'll tell you, well, what you need. So when you're on site and you want to find out several things, you want to see what size system you've got, you want to know how old it is, etc. That information is available on the nameplate. And so two things, if you want to find the nomenclature to determining the size, that's going to be in the manufacturer's model number. And somewhere in that is going to be a code for the size of the system. In this particular case, which is a Carrier, the nominal cooling capacity, that's your tonnage. So if you see that 036 and you do the math, and remember, 12,000 BTUs per hour equals 1 ton of cooling. So when you talk about what's a ton of cooling, it's 12,000 BTUs per hour. So if you take that 36 divided by 12, that's 3 tons. So you see in that code. Now you would have to go to the manufacturer's website, but every website has that nomenclature breakdown in it. So you can go to the Carrier website and look up that nomenclature breakdown. You're going to know your size of your system from the nameplate data. Then the second thing, and this is a handy website that I inform agents of. This is where we go to find out everything we need to know. And if you look down at the blue, you'll see there's an HVAC index and there's a water heater index. So what I'm about to tell you is good for nameplate data on an HVAC system or on a water heater for determining the age of the system. So that you see that URL up there, building-center.org. That's your website. But I guarantee you right now, if you went into Google and Googled Carrier HVAC age, your first or second hit on Google is going to be Building Intelligence Center. So it's super easy to find. Just, whatever manufacturer name, A.O. Smith water heater age. You just simply cannot not find this information, but building-center.org. And then when you go into that, again, this is for a carrier system. When you go into that, it's going to have, and sometimes several generations of serial number. Now, remember we were talking about model number nomenclature that you had to go to the manufacturer's website. This website, you're keying on serial number, and all of the systems have serial numbers. All your HVAC and all of your water heaters have serial numbers. So if you go into carrier, you see right here where it says style 1, there may be multiple styles, but one of them is going to match what you're looking at. In this case, you're looking at 4 numbers, a letter, followed by 5 numbers. In this case, the first 2 numbers are the week of the year it was built, and the second 2 numbers are the year. So that's a 2006 system. And then the A is probably which factory it was built, and then the other numbers are just sequential. So almost every manufacturer is either the first 2 numbers or the second 2 numbers. Now and then you'll get into some letter codes, but again, you go to this website and you go to that system. If you go into the URL and you go to that index, then you're going to search for it by manufacturer. Fewer steps are going to be if you Google carrier HVAC age and then look for the link to Building Intelligence Center, you're going to go straight into this section. So you're going to have fewer clicks. And that's an easy way to always find the age of the system. And then you're same for your water heaters. So fresh air ventilation, we talked a little bit about, and we mentioned it in sizing too, that houses used to be just real loose, nooks and crannies. Air could get in wherever it got in, under doors, around windows. Houses just weren't that tight. And as you were doing things in the house that needed more air, it wasn't a problem because the aggregate volume of air you could draw in through all the nooks and crannies of the house was more than enough when you were drying clothes. When you run a dryer, you're very dependent because you're sucking air through that system and blowing it out of the house. That more air has to come from somewhere, because if you're not moving air, you're not drying clothes very well. You're heating them, but you're not drying them. It's the airflow that really gets the job done in a short period of time. That air has to flow from somewhere. Same thing with a hood vent in the kitchen. When you're sucking air out of the house, that air's got to come from somewhere, because if you're not moving air, you're not going to be moving the moisture or the smells or whatever you're trying to get out of the house. So houses got much tighter, so that air has to be made up, but you want it made up in a controlled manner where you have a system. And in this case, what we see is typically the system on the left, just a simple, straightforward fresh air system, where you draw that air from outside, but you draw it straight into the return duct of the HVAC system, so that before that air is introduced into the home, it is brought through the system and conditioned when that system is running. And so we see them very frequently. Now, this particular one shown in a lower level or a basement or whatever, we almost always see these systems in the attic. And you'll see, actually, I need to load up some pictures so you see exactly what I see. But in the attic, in addition to the HVAC equipment and the zone board and all, you will have another control module in the attic. And if you follow, and it'll have a ductwork into that system. If you follow that ductwork, you'll see that it goes over typically to a sidewall or to the roof in the attic, where you draw air in, and then you follow the ductwork out of that, and you'll see it goes into the return duct. And we show those in the report when we do our inspections, and they're there so that a client can see what they've got. But that's how you make up air in a controlled, conditioned manner in a very tight house when you're running things and you just need more air in the house. So refrigerants, agents know, and you guys tell me if you're at where we're at in it these days. But R22 is going away. Now, R410A has been around long enough now that more and more of your systems, I think it started by 2010, I think all of the newer systems were coming with R410A. It started actually before that, but I think by 2010 they weren't installing any more systems with R22. So the majority of your systems with R22 probably are cycling out now. But this was a result of part of international agreements on eliminating hydrofluorocarbons out of products that were thought to be damaging to the environment. And R22, we still see it. We still see systems in operation with R22. R410 is the non-HCFC replacement. Now, the thing about it is those systems that were designed to use R22 cannot be converted to R410. And when you're looking at an older system, especially when those systems, you're getting into now 15 and 20-year-old systems, clients should be made aware when the systems are older. Now, if you're talking about a 15 or 20-year-old system, it's outlived what the HVAC guys say you would get out of it anyway. So a lot of this where we are today will take care of itself very soon. But in the meantime, you see that no production or import of 22, except for equipment manufactured before January 1st, 2010. So at 2010, now we're 10, 11 years into production of equipment without R22. So this probably will go away on its own in the next 5 or 10 years. But as you are looking at older homes with your clients, just be aware of some of these things. And no production or import of the refrigerant. In 2010, no more production or import of the equipment using it. Now in 2020, there was no more production or import of the refrigerant itself. And most people had stopped importing it anyway. And in 3030, all HCFCs go away. So I'm told this is very old now. What's happened is R22 has gone up exponentially as it gets more rare. And in fact, what you'll find today is that when they saw this coming, HVAC companies started capturing that refrigerant rather than letting it escape into the air as they repaired or replaced systems. So there's a whole market, and what you would find today is recycled R22, where they captured it. I guess these guys sell it to a facility somewhere who then filter it, clean it, can it, and sell it as recycled. So that recycle at that time was averaging 25 or 30 a pound. I'm told it's closer to 40, 50 a pound now versus $4 a pound for R410. So there's, sometimes an economic argument against trying to keep a system in service. There are alternative refrigerants, and I've only heard discussion about their use in context to home warranty companies. And so this is something for agents to be aware of, because I know a lot of times clients are buying the home warranties as a safety net for what ifs in their home. And we'll talk about these alternative refrigerants some, but the only time I've heard of them being advocated for use is when a home warranty company is trying to keep an existing system operating versus buying someone a new one. So do be aware of that. These alternative refrigerants give you an ability to keep the older units operating. They void all manufacturer warranties, but you're talking about systems that are long out of warranty anyway. And they're best suited for those systems that are out there, non-ozone depleting. And when they're given an ASHRAE number, they are designated with an R, like the R22 and the R410A. They've been reviewed by those industry committees and safety classifications been assigned. They can't be combined with R22 or any other refrigerant. The most favorable choice, the one that performs most like R22, also requires a complete oil change of the system. And the refrigerant has oil in it, and that is primarily to lubricate the compressor as the refrigerant passes through. That's how you keep the compressor lubricated, by the oil that's mixed in with the refrigerant. And it requires an oil change. The R22 is mineral oil, and the alternative is the polyester. And there's a URL link to a website for some information there. So if we look over here at this R407C on the right, that is the alternative that performs most like R22, but you'll see at the bottom, it does need an oil change. And then you get into what is it, what are we talking about in the real world? So I've had conversations with a number of HVAC contractors, and they're pretty much to a man dead set against it. So we're looking at the alternatives can be used, but will a given HVAC contractor do it? If you are looking to have this done, is the HVAC contractor you're working with willing to do it? And some of the reasons that I've been given for these guys shying away from it is they say it results in 80% unit efficiency at best. So however, whatever 100%, whatever the unit was working at before it was done, you're only going to get 80% of that after. So the system's got to work harder. The utility bill is going to go up. The house may not be as comfortable. People are going to be unsatisfied. And HVAC contractors really don't want to hear it. And they just may not be willing to take on that liability. And I'm also told that it only takes a quarter teaspoon of the wrong oil left in the system to gum up the whole thing. So there's just, I'm hearing that the warranty companies use them as a tool to keep a system running, but there's a downside to that to be aware of. And that's the whole story today. Can I answer any questions for anyone? So once again, we've done such a stellar job that we answered every question you possibly had as we went along.
Very informative. Thank you, Ed.
You're welcome, Joanne.
Very much so, and it's a lot of information for sure. It's one of those.
It is a lot of information. I tried to make this in a way that wasn't technically overwhelming, but it's hard to really give you a lot of good information you need without it maybe being more technical than you want. But the beauty of it is having the recording, having the presentation as something to refer back to, and you've got me on the other end of the line. So if you guys have any questions or any concerns at any time, feel free to reach out. If you don't get me live, you'll hear back from me very shortly.
Absolutely, because it's one of those where I don't have anything in the moment, but I'll definitely be glad to have the slides to look back at and kind of re-examine some of the things.
Yeah, when you get into these homes prior to 2010, you'll run into some of these issues where you're looking at a system. But very frankly, what we find is these HVAC systems, if they're, and it's how well has it been maintained? A, has it been maintained? And B, how regularly and how well? You can keep these systems running a long time. We see them performing properly. They're 18 and 20 years old. HVAC contractors will tell you they'll last 12 or 14 years. Well, we're looking at something, and that's generally maybe true on the average. So be aware if your client is looking at something that's 12, 14 years old, well, it may last 6 years or it may last 6 weeks.
That's actually my house right now.
Yeah, it's hard to say. So anyway, good to see you guys.
Thank you, Ed.
Yeah, thank
You're
you,
welcome. There's my
If you-
contact info. That is my cell number there and my email address. So let me know how I can help you and let me know how I can help your clients.